All right. Hello and welcome to Racks, Brackets, and Obstacle Detection with KUKA AMRs. Key takeaways of this session include rack and bracket integration, some best practices for designing and implementing racks and brackets to optimize payload handling and workflow efficiency. We'll go over advanced obstacle detection, leveraging sensors and software to navigate dynamic environments, and some real-world applications. My name is Jules, and I'll be your host for this session. Thank you for joining us today to hear from Mohammed Shatit, AMR Sales Application Engineer from KUKA Robotics. If you have any questions during the presentation, please feel free to type them in the chat box or specifically the Q&A tab found on the top of your screen to the right. We'll address any questions that come in at the end of this session. Now I'll pass it on to Mohammed.
Okay. Thank you, Jules. Thank you, everyone, for joining us today. Like Jules said, today we're going to be talking about racks, brackets, and obstacle detection. So we'll go over what racks, brackets are, what do they mean, how to configure them, how to implement them, and we'll show some examples. We'll also talk about obstacle detection with KUKA AMRs and safety aspect of that. So let's go right into it. So before we start, I'm going to show you KUKA mobile platforms, what they look like, dimensions, and so on. We'll talk about the different station types, and we'll also go into some design consideration. We'll implement a rack, and we'll configure obstacle detection and safety, and then we'll go over some examples, like I said. So KUKA mobile platforms, we have different platforms. We go from 250 kg, which is the KMP 250p on the right, and we go all the way up to 3000 kg. The 250p, 600p, and 1500p are all differential drive, so they drive forward, backward, and they rotate on the center. The 3000p is omnidirectional, so it will drive forward, backward, it will rotate on the center, and will also drive sideways and diagonal. All KUKA mobile platforms have an integrated lift on top of them. They have different strokes for different platforms. And we also offer an application interface for power, safety, and communication, as well as mechanical mounting holes. Here I show the different dimensions for the 600p on the left, 1500p in the middle, and the 3000p. So this is the length, width, and height for the different dimensions, and also for the different models, and also the lifting strokes for these. So when you're designing your rack or bracket, you want to know which KMP type you're going to be using, so you design it for the correct size, correct type. So station types, for you guys who have worked with KUKA AMRs before, I'm sure you've heard of brackets, holders, racks, carts, containers. There's a lot of terminology there. So I want to go over some terminology so we know what we're talking about here. So I'm going to start with from the left, bracket or a holder. So this is a fixed stand that an AMR would drive into to pick up a container and drive out. So this is a fixture. It's usually not moving. It's fixed on your floor, and it has a load on top of it where the AMR can come in and pick it up and leave. This is usually paired with a tray, and we'll go over what the tray means, but it basically could be your pallet or bin on top of the bracket or holder. In the middle, we have a rack. So this is a frame. It has the legs attached to it. So when the AMR comes in and picks it up, it's going to pick it up off the floor with the legs and transfer it to an empty spot on your floor. A cart, so this is basically a rack, but with wheels. We like to differentiate between racks and wheels so we know what we're working with. In the software, we also differentiate between the brackets and racks and containers. So a bracket node is basically your empty spots. This is where your fixture is on the map, the X and Y position, and it could have a load on top of it. It could be empty or it could be full based on at that moment of time. But usually this is where your fixture exists. A rack node, this is basically an empty space in your floor. There's nothing there. There's no fixture. It's just position, XY position for
for your racks to exist in. And the container, so this is the transferable object by the AMR. This is the rack tray that will go on top of the rack nodes and bracket nodes. So this is what the AMR will be carrying and going from point A to point B. So there is some design consideration when you want to design a rack or a bracket for KUKA AMRs. There are a lot of numbers here, but KUKA AMRs are ISO compliant. So when we ship the AMRs out of the factory, we follow the ISO numbers. There is also some KUKA specific guidelines. For example, L1 for the lift, we require some spacing for different AMR types. You can see here 50 clearance, 50 millimeters clearance for the 600p and 25 for the 1500p, and then 20 for the 3000p. So you have different dimensions here that you want to follow. I'm not going to go into all of them today. And another interesting one is L3. This is the space that you want to maintain between the AMR and the bracket you're going into or the rack for safety and also accuracy.
Hey, Mohammed. Sorry to
Yeah.
jump in real quick. Just because it's covering a little line right there, there's a tiny pop-up at the bottom for sharing screen if you just want to hide that. Perfect. Thank you.
I thought you can't see it. Thank you. Okay, so we talked about L3. This L3 is also, so you want to consider this L3 dimension when you're designing your top module as well. So when you have a top module that extends over the AMR dimensions, you want to take that L3 dimension from the side of the top module, the sticking out point. You don't want to go from the AMR. Same thing here on the left when you're if the bracket is higher than the AMR. So you want to consider the top module when you look at these dimensions. You also want to, this is more for racks, but you want to consider rotations. So if you want the AMR to rotate under the rack, you want to have some safe distance inside the rack. And I don't show the numbers here, but we have a lot of documents that go over these dimensions in details and what they should be in each different scenario. All the AMR, all the KUKA AMR KMPs have an upper camera for the QR code. So if you want to do QR code recognition or container recognition or adjustments for position, you want to consider the minimum and maximum distance for that camera. If you're not using a QR code, then you don't have to take this into account. There's also some requirements for the legs. So there's a minimum width for the 3000p, minimum width for the 600p and 1500p. We cannot do circular legs. We require the legs to be rectangular. And then we have some requirements for ribs because the scanners, which is what we will be using to locate these racks, is at the 170 millimeters or 6.6 inches off the floor. So we want this point plus minus 50 millimeter to be consistent. So we don't want it to look like this, where each time we're looking at a different cross section, depending on the floor. And then you don't want these legs to be laser absorbent, so we can actually look at them and see them. For docking into these stations, you want to also follow the minimum distance and maximum distance. So this is how far your AMR is from the station before it goes into the station. Basically just some numbers here, and they're different if you're doing object detection or reflector detection. You wanna always account for this. So now that we went over these numbers and what we should look out for when we're designing racks and brackets, I will show you how to create a rack and how consider these dimensions, and also how to configure it in KUKA AMR suite and put it in KUKA AMR fleet and use it. So the requirements for this rack is to follow the ISO and KUKA guidelines. We also don't want to use any top modules. And I want the AMRs, it's going to be for the 600p and the 1500p. And I want both AMRs or KMPs to rotate under the rack. So I want to account for that as well. I want to use a QR code, and then we'll model the rack in KUKA AMR suite and implement in KUKA AMR fleet. So to save us some time, I went and looked at the dimensions for the 600p and 1500p, and I designed my rack, and these are the numbers that I came up with. So 1100 millimeters from the inside legs, from the inside, from one leg to the other, and then 1200 millimeters from outside to outside. And so that means the legs are 50 millimeters, which higher than the minimum, which was 40 millimeters. So, and this also, if we look at the 1500p, which is 900 millimeters wide, and then we're adding 100 millimeter for the L3 dimension that we talked about, that's going to give us 1100 millimeters, so we satisfy that requirement. This is the length. We have 100 millimeter on front and back, so that's also covered. And then 320 millimeters. So this is going to work for both the 1500p lift stroke and the 600p. The 600p is going to be a little bit awkward because the leg is going to be a little bit closer to the floor, but it should be should still be okay, depending on your floor, obviously. And that's because of the difference of clearance for the 1500p and 600p, and also the difference in lifting stroke for these models. So I said I want to rotate under the rack, so I'm looking at the 1500p because that's the larger one, and I'm making sure that I account for 100 millimeter when 100 millimeter of distance when I rotate under this rack. So that's also accounted for. So now I know what so I designed my rack in CAD. I know what it's going to look like. I sent the model to be manufactured, and now I have my rack on the floor. I want to have it work. I want to have the AMR go in, pick it up, and transfer it from different points on the floor. So for this, we're going to be using KUKA AMR Suite. And if you guys don't know, KUKA AMR Suite is a configuration tool for KUKA AMRs. It does a lot of things. This is where we configure the network, where we map, obviously configure the racks, brackets. This is where we do obstacle detection, parameter changes, calibration of different peripherals. So it does a lot. We're not going to look at all of these things. We're going to look at creating a rack today. So this is what KUKA AMR Suite looks like. Here I'm in the navigation page, and I want to go to rack model, and then I want to head over to model editor, and I'm going to see this page that you see on your screen now. So we're going to go over some of these settings. I'm not going to cover all of them because there is a lot. If you want more details, we can. You should be looking at the KUKA AMR Suite manual for these details. So you have, for the model type, I want to select the storage rack because that's my station. You also can select a holder or a tray. Holder we set as a bracket, and a tray is just a container. I'm going to select both sides because my rack allows for both AMRs to go in from both sides. So I can accommodate for that and be able to rotate. There are some advanced settings if you want to select, if you don't want to do both sides, or you don't want to do longer and shorter, you want to select just one side, you can do that as well. You can select a standard and irregular geometry type. So the difference between these things, if you, this is just for the creation of the model type. So if you select standard and you put in your leg size and width and length for the rack. It's just going to create a simple rack for you with 4 legs with the dimensions that you put in. If you have a more complicated rack, for example, a rack with 6 legs, for example, or that it's not uniform and that the legs are in different positions compared to each other, you want to do irregular and then put in each point for each leg yourself. So it accommodates more complicated models, but also requires more work on your side to put in this model and create it in KUKA AMR Suite. So my rack is just 4 legs. I know the dimensions. I'm going to choose standard. I'm going to put the dimensions in there. There's also some advanced settings. We don't recommend you changing these. If you do want to change them and you think you might get better detection or so on, please contact us before you do. This is what they mean from the manual. So now we're in the section where I put in my file name. So I'm going to call it webinar_rack. I will remember this name because when I go into the second program, KUKA AMR Fleet, I will have to use the same name. I will reference the same name in that. I will put in the length, width of the rack. There are some settings here also for more advanced stuff that you can do with the rack. So you have a hit ratio that you can change. You can change minimum match like numbers. So if you only want to detect 3 and that's okay for you, or how many points per leg you want to detect. And if you want to do an offset for this rack, you can do that as well with a QR code or without a QR code. I'm not going to do any of that. I'm just going to put in my length, width, and I'm going to put my legs dimensions as well. So this is what it looks like. They're all 50. And then I'm going to click on draw, and I'm going to see my rack here on the screen. So you can see the length and width all match to what we put in. I can go in from both sides, so shorter side and longer side. You can see the AMR is approaching it from all directions. You can see the legs. There are filters around them by default to ignore these legs, and we'll talk about this in the obstacle detection section. But yes, it's basically that easy. So I created my rack. I can. This is just me showing you that you can extend this leg filter if you have a wheel or something. But if you're satisfied with your rack, you save it. You go to model list, grab the model, select your AMR, and upload it to the AMR. So now the model is created. It exists on an AMR, and you can send it to all AMRs that will be used in this rack. So now I have the rack. I created it. I know what it looks like. I want to use it in KUKA AMR Fleet. I want to put it on the map and have the AMR go and pick it up. So this is KUKA AMR Fleet. This is the fleet manager. This is where you will be sending missions. This is where you put your positions, X, Y, and so on, create your processes. We're going to go to scheduling here. We're going to go to container model. We're going to create a new model here. We're going to put all this information, basically the same thing that we had in suites. We're just going to reference that. So you can see here I have the model code the same without the extension, without the file extension. I'm going to select the AMR type that I want this rack to work with. So we set 600p and 1500p. The obstacle detection plan, this you can ignore. In most cases, this was an old feature that we don't use anymore. So this can be ignored going forward, unless you have a very old version of an AMR. I put in the rack length, width, container heights, chassis heights. Some of these are not required, so you don't have to put them in if you don't want to, but that are there. So I put them in, and then I can reference them in my upstream system if I want to. So I have, and that's basically it. That's my model. Now I want to use my model on the map. So I'm going to go back to scheduling. I'm going to go to my districts, edit the graph that I'm working with. And I know this might be a little bit in depth for the people who haven't used KUKA AMR Fleet before, but bear with me here. So we're going to go into the node. We're going to edit the node, go into function, and create a rank node, and select the rack model here. Once I do this, I save, and then you can see here on my map, the node is going to change to the rack node icon that we talked about earlier in the presentation. I want to save the graph, and I want to add a container on top of my rack, because if you remember, this rack node that I selected is just basically me saying this point in space is going to be able to accept containers. It's a rack node. It's just an empty space. It doesn't have anything on it right now. But now I want to add a container. I want to say this position has a container on top of it. There is a rack physically there. So I want to go to scheduling, go to container, and I want to insert a new instance, if you will, of that object that we created earlier. So I'm going to select which building, which layouts, which district I want to insert it to. I'm going to select which model. So this is the object that we created earlier. I'm going to give it a container code. So container code is different than container model. Container model is the blueprint, and the container code is the different objects that you build off that blueprint. So validation code here is my QR code. So I'm going to put rack1, and then I'm going to go in and use KUKA software to generate my QR code and put it under the container properly. I'm going to specify my container direction here. It's -90 based on the map. And if you don't know what these directions are, this is what they look like. They are relative to the map. So positive X is this way, positive Y is that way. So this to help you specify which direction when you enter the container. And this matters because the length and width of the rack is not the same. So when I put my rack on the map, it's going to matter I put it correctly, because when the AMR goes in and to pick it up, it needs to know what it looks like. Otherwise, it's going to have problems detecting it. And then I'm going to specify the node number that I want to enter the container in, and that's 25. There are some parameters here for return by default, yes, no. Well, there's more information on this. I don't think I've ever used this before, but there's more information in the manual, and you can also select the status of the container for empty and full. And you can also put some description here. So once I do that insert, I can go back to my map monitor, and I can see there is a container icon on node 25. And that's the rack node. So there's a rack node on 25, and there's a container on 25. So this is what it will look like, and here are the details that we put in. So this is me seeing this live. So that was very straightforward. I would say there are more complicated racks, obviously, and brackets, and I will show some examples of these at the end. But in most cases, if you understand what you're doing, you plan your steps and go through them, I think it's pretty straightforward. Now to the, I think, most confusing section of obstacle detection and safety. I get a lot of questions about this topic. So I want to go through it today, and also kind of goes hand in hand with racks and brackets, and hopefully clear up some confusion. So KUKA AMRs have different safety functions. there is safe obstacle detection, which uses the 2D scanners, 2D safety SIG scanners, and 3D cameras. And I want to mention here that the 3D cameras are not safety rated. The SIG scanners are safety rated, the 3D cameras are not. And then this safe obstacle detection section is based on the AMR size and container size programmatically. And it's controlled by KUKA AMR OS, the operating system on the AMR itself. And this is more used for machine safety and obstacle avoidance. It can make the AMR stop, but that's not the design intent. There's also speed monitoring, safe speed monitoring. This is PLC based. It's monitoring the motor feedback, safety field cases, and the lift. And it's basically self-explanatory. It's monitoring the speed of the AMR through the PLC. There's also emergency stop. Obviously, you have the obvious. You have your e-stops buttons on each corner of the AMR. And you also have the 2D scanners. These are safety rated. They have warning and protective fields. So warning will slow you down. Protective is going to emergency stop the AMR. So it's going to stop it. These scanners are configured to have different cases. And there is a different case active based on the AMR speed, lift status, direction of travel, and so on. And these cases are controlled by the safety PLC. So this whole thing is safety rated. This is your safety function. This is your real safety function of the AMR. So if we combine the scanners and cameras, this is what they will look like. The camera goes up to 2,000 millimeters roughly, so around 6.1 feet. This is the angle. This is what it will be monitoring basically. This is the FOV. And you also have your scanners, so the 360 view between the two scanners. It is also important to mention that the 3D cameras can only detect 80 by 80 by 80 millimeter obstacle dimension. So anything smaller than that, we cannot detect. The bottom section here is just showing the different cases, and I will show more of that in the next slides. But this is just to show that the different cases are based on different speeds. So, and they're divided into 4 sections. So velocity 1 uses a different safety case, which basically is a different safety field. And velocity 2 uses a different one that's a little bit larger. And the fields go larger as you go faster. This is what the safety fields look like. The orange is the emergency stop. The yellow is a warning field, so the slowdown field. These scanners are SIG scanners, so we want to use Safety Designer engineering tool to configure them. When you touch these fields, you want to make sure your requirements. We recommend that you follow the ISO requirements. We follow the ISO standards, but if you're allowed to change them however you want, but you should always do your own risk assessment and make sure that these fields are truly safe for what you're doing, for what your application is. You want to make sure that you cover the rack, the AMR. If you have a top module that's extending over the AMR size, you want to make sure that you cover that. There are different fields, like we said, loaded versus unloaded, so the lift status, and different fields for speed, travel direction, and there's also some fields that are special cases. So these are usually not triggered unless it's a special case, and we'll go over what these special cases are. So this is what Safety Designer engineering tool looks like. You can use the latest. When you go into a project, you'll see for the 1500p, you'll see if laser, front left laser, rear right laser, and also the PLC. These are the 1500p different cases. So I think this one has 16 cases, and you can see the name here. It's each one is for a different case. Basically, there's a standstill pivoting with unload, so that means you're not moving and you're not loaded. That's the field that you're going to be using. Also, it's for pivoting. So if you're rotating, so I should say if you're not going forward or backward, you're just standing still or rotating on the center. That's the field you're using for lift case down. There's one with lift case up. Then you also have a section for forward speed, and it goes into speed limit 2, 3, 4 for unload, and then 2, 3, 4 for load. And then you also have a section for backwards. So yes, there is 16 cases. Each serves a different purpose. The app case 1 and app case 2, so these are case 15 and case 16. These are the specific cases that we talked about. These are triggered automatically when you're going into a bracket or a rack. So this is when you're doing the docking motion. They're also triggered when you're docking to a charger, you're going into an elevator, and those type of special actions. Specific case 1 is for unload states, unloaded state, and specific case 2 is for the loaded states. And you can, on the fleet manager, you can configure some edges to be triggered manually to use these. But you want to be very careful where you do this, because the AMR will be limited in speed to 0.3 meters per second, but again, these cases are very limited in size, so they're only 100 and I think 20 millimeters around the AMR. So please take that into account. The manual shows you that if you go into the 1500p manual, there's a section that shows you what to consider when you're doing overhanging loads. So if there's a load that overextends the AMR, that's going to affect the safety fields, the default safety fields, because the default safety fields are configured for the default AMR size. If you put a top module that is bigger, then the safety fields are not valid anymore. So you want to make sure that you extend your safety fields by these parameters, but usually just by the extension of that top module. And there are more details in the manual than I can show here. Other thing that you want to consider is the break-in and reaction time. So you can't just have your safety field covers just the top module and that's it. You want to have some distance or some space. So if anything comes in front of the AMR, you want to have enough distance for the AMR to stop for the different speeds that it's going at. So consider overhanging loads, please. So I think that's the safety scanners. 6 safety scanners. You want to use Safety Designer to configure them. You want to do your own risk assessment. When you do that, you want to consider overhanging loads and the loads that you're carrying. Now we're going to go into the obstacle detection. And when I say obstacle detection, I say scanners and cameras. They're both. It's not just the camera. I think that's a common misconception. There are different obstacle detection I guess, programs, if you will. The global map based, this is using the global navigation map. This is your base map, the map that you create, and the obstacle map. So anything in your floor is, any object is considered an obstacle. And this will
the AMR will detect these obstacles when it's going through a path. And it will enable replanning or avoidance maneuvers in some cases. There's also the local robot-centered program. This is using the AMR coordinate system. So this is monitoring the obstacles around the AMR. It's not looking at the map, it's just looking at the camera and scanner and looking what's next to the AMR and deciding if it needs to stop or it needs to do obstacle avoidance or path replanning. This is the architecture of the obstacle detection. So again, it uses the laser data and camera data both for the obstacle detection module. It also considers the static map that you create with the scanners, the time travel sensors, the cameras, and ultrasound. And basically based on this graph here, it decides what to do. Does it need to stop? Does it need to do obstacle avoidance maneuvers if these are enabled, and so on. I'm not going to go into every single block of these, but this is what the obstacle detection architecture looks like basically. The AMR knows its size. So it's programmed to know its size when it's doing obstacle detection maneuvers. It knows how much it needs to deviate from the path. It knows when to stop. And there are different cases, obviously. So it depends if it's payload on the payload status. So if it's loaded or unloaded, it depends on the padding that you specify on the AMR. If it's carrying a container that's larger than itself, then it's going to add that padding to the container size. And there's also different paths that you can specify on the edges, the common path, narrow paths, or special paths with basically going into brackets, racks, or chargers and elevators, and so on. There is a concept of invalid region area. So this is invalid area or ignore area, you can call it. This is an area where it's around the AMR with a certain distance, and the AMR is going to ignore anything that comes in this area. So rack legs are going to be ignored. Anything hanging down from top of the AMR is going to be ignored. By default, the invalid region area for the unloaded AMR is basically 0. So there's no invalid region area. We're not ignoring anything. But for loaded states, we need to ignore the rack legs so we don't see them as obstacles and stop. That's basically the concept. You can change this invalid region area if you want to, but we recommend that you not exceed more than 100 millimeters. There is your rotation area. So this is taken into account when the AMR is rotating. It knows its diameter, and it's going to calculate how much space it needs to rotate. So if there is an obstacle here, for example, the AMR is not going to finish its rotation, and it might try to do obstacle avoidance or just replans the path. And obviously, these diameters are different for unloaded and loaded states. There's the camera height and I guess low and high detect Z. So how far the AMR can see below it or below the camera. So 0 is the camera level on the AMR. Low detect Z min is how far it's looking below, and high detect Z max is how far it's looking ahead or high. So by default, it's looking 200 millimeters down to the floor, and it's looking 2,000 millimeters. You can change these. In most cases, you don't need to. When you're going into a rack or a bracket, they're by default limited, so we can go in. So you don't have to modify them unless you need to. And I think in most cases, you don't need to do that. The AMR contour definition, like I said, the AMR knows its size.
But when you put a top module on top of it that extends the AMR size, it doesn't know that. So you need to tell it that this is your new size. I put something on top of you that's bigger. So you need to go into KUKA AMR suite and define this new size. So we support two different modes, I would say, the symmetric and asymmetric. So symmetric is when your extension is the same on front and back and left and right. Uh, so you have X and Y. This is where you put your new size. Or you can do, if it doesn't match front to back or left to right, you can do different extrusion for each side. So you have to specify this. Otherwise, the AMR is not going to take the top module into account when it's doing obstacle avoidance. It doesn't know its size, so it tries to do something, and if it sees an obstacle that's not at the height of the scanner, and maybe it's on the side where the cameras don't see it, it's there could be some blind spots where it could hit that object. So you want to have that considered. So these are some examples for top modules that we've done before. Obviously, the one on the left is not symmetric, so we use the asymmetric extension because we wanted to specify on the front only. The one on the right is symmetric, so you just put in the new X, and I think it just overhangs just a little bit on the Y, so we did that as well. But this is what you want to do when you have top modules that look like these. This last section I want to cover is obstacle detection configuration. For people who have worked with KUKA AMRs before, especially in the past, we've had different ways to configure obstacle detections. We did them in, obviously we have the default obstacle avoidance plans in KUKA AMR Fleet. You can configure special ones on the paths. You have your KUKA AMR suite parameters for special tasks, and we've done it in Docker Compose. We've also used the KUKA AMR files to do them. So there are a lot of different ways that we've used in the past. Some of them we still use, some of them we don't. So I want to go over this and kind of highlight when to look at which and in which case. So we have a diagram here that we've received from our global colleagues that specify when to use which parameters. So they break it down to KUKA AMR Fleet. This is our fleet manager, or VDA 5050. So if you're using VDA 5050 and you're doing a normal task, basically going from point A to point B, and both points are normal nodes, just positions, you want to use the fleet map editor to configure the obstacle detection. If you're going into, if you're doing a special task, going into a rack or leaving a rack holder, elevator charger or rotating task, you want to use KS settings for that. If you're using KUKA AMR Fleet, then we're going to break this down into different versions. I would say that this top branch is the new version. So this is KMR OS 2.3.2 plus and KUKA AMR Fleet 2.3 and plus. And this is easy. If you're using a SLAM or QR code, it doesn't matter. If you're using a normal move task, you want to use the fleet manager. In this case, it's KUKA AMR Fleet map editor to configure your obstacle avoidance. If you're doing a special move, you're entering, leaving racks, holders, elevator, charger, or rotating tasks, you want to use KUKA AMR suite settings. So basically, very similar to VDA 5050. This is where the confusion comes from for people who've used the AMRs in the past. We've had it separate to these different branches, QR code versus SLAM, normal tasks, and then also you have branches for holder and also rotating tasks are different, charging tasks. We're not going to focus on these because most people are on the upgraded branch now.
if you still need help with these, please reach out to us and we'll make sure to help you with this. But this is what I'm going to show, the Fleet Manager and the KUKA AMR settings. So you have your default obstacle avoidance. They're specified here. You will see that it's default. So if you don't have anything on the edge in your map, it's going to be using this plan. And these are the default parameters. You can change them, but there are some restrictions on how low you can go. I do not recommend changing the default one. I recommend using special ones if you need to for specific cases. I would leave the default one as is. If you want to create a new one, you go into the same page, scheduling, obstacle avoidance, and then you go to new and you create a new one. I'm creating a new one here with calling it my custom 600p obstacle avoidance plan. I put in some parameters that I would like to use. I can enable or disable the camera. And then I go to the map and edit the path and select my plan, like you see here. I'm kind of going fast a little bit because we're running out of time. But that's how you do this, creating a new plan. And this is for normal tasks, for points A and B and being normal. You save, and that's it. That's how you specify a new obstacle avoidance plan. If you are doing a special task, you want to go to KUKA AMR Suite. So sorry, these are what the special tasks look like: going into a rack with a container on top of it, leaving, brackets, chargers, elevators. You want to go to KUKA AMR Suite, base info, obstacle avoidance, and you have a list of parameters that you can change. For containers or racks, you have Z max, Z min, X, and Y. And these are the default. So let's say your rack by default is a little bit lower. We are considering that we have a padding of 120, so we're looking 120 millimeters from the camera level. If your rack is lower, then the AMR is going to try to go in. It's going to detect the rack, but it's going to see it as an obstacle. So you want to lower this down a little bit. So that's for racks. If you have a bracket, you also want to change that based on what your bracket dimensions are. And sometimes people have supporting plates on top that kind of go closer to the AMR as it goes in and so on. So this is where you go to change these parameters. And you will know when to change these parameters, because when you send the AMR to go to pick up a rack or a bracket, or go into to pick up a rack or go into a bracket, it will tell you that it sees it as an obstacle. So immediately you would know to come here and change these parameters. So that's basically it of configuring and implementing a rack. Now I want to go over some simple examples or quick examples, and then we'll hand it over to questions. So some racks we've done before. This is for a customer. This is what the model looks like. Very simple, just like what we created today. This length, width, we can go in from all sides. We specify the rack legs. It's great. It works well. No problems with it. This one is a little bit more involved. The legs are a little bit different for each rack, so we had to play with it a little bit, but it's honestly not that complicated. It's just that this leg is shared between this rack or this bracket, sorry, and this bracket, but it can be done. This is what the model looks like. We've done some more complicated stuff. This is our tandem application. So two AMRs are moving this rack together. They're working in sync, but
that doesn't mean that the rack needs to be complicated. It's still 4 legs. Sizes are based on the requirements, and this is how you create it. We want to go in from the shorter sides, and that's it. We filter out the legs, and that's pretty much it. I've seen some brackets that look like this, and we also can model them and doctor them. This one does not follow the ribs being uniform across the height of the bracket. Sometimes the position is off, sometimes a little bit from what I've seen, but it's still okay because they have enough space for the AMR to go in and drop the tray on the bracket. But if you require more precision than that, then you want to make sure that these are uniform. And also they kind of combat that with the guiding pieces over here. This is also another complex model, I would say. So this is the back, and these are the fronts. So this is the fence here, and then there are legs on the inside. So we modeled that to look like this. And then also, I think this has an offset on it a little bit. So because we're not docking to the center, we're going in a little bit inside the bracket. That was all of it. I hope I didn't go too fast for you guys. And then I'll pass it over to questions.
Yes, thank you. Thanks for sharing your presentation with us. So we can go into some Q&A. I see we have a bunch of great questions that came in. And just a reminder, you can still send them into the Q&A. And if we do not get to all of them, we will follow up with those that did submit. Or if you have an additional questions, I will go ahead and put Mohammed's email into the chat. But let's go ahead and get started. So the first one is, what is the best way to deal with the blind spots created by the legs of the rack?
This is a good question. There isn't a way other than filtering them out. So like we said, KUKA AMR fleet is going to filter these, sorry, not fleet, but the system is going to filter out the legs from the obstacle detection side. But for the safety side, if you see by default, there are notches for the legs. And if your legs of if your rack legs don't fall within these notches, you want to make sure that you move this notch to match where that falls. It's a blind spot. You have to consider it. It has to be on your risk assessment, I would think, and it's just something that you have to deal with.
Awesome, thank you. Another one here, is there a way to disable path replanning to make the AMR wait for obstacles to clear?
Yes, so you can disable obstacle avoidance. So if you don't want the AMR to go around the obstacle, you can disable that, then it would wait. There's also path replanning. So if the AMR waits for a long time and the obstacle doesn't move, it's going to try to find a path on the graph. It's not going to go around the obstacle. It's just going to go back and find another path. You can disable both of these.
Perfect, thank you. A dual one here. How far does the camera look and detect obstacles reliably? And then does it do any obstacle classification distinction between moving or non-moving obstacles?
The camera looks up 2,000 millimeters high, so 6.1 foot, and it looks 4 meters ahead. That's what it's looking at, but that doesn't mean that's the obstacle detection range. That's not when it's going to stop. Currently, the camera doesn't know if the obstacle is moving or stationary.
Thank you. Are the TOF cameras part of the 3D cameras you showed, or are they separate?
The TOF is the camera itself. That's the time travel sensor. That's the camera.
Perfect. What are the safety ratings?
So the safe obstacle detection part is PLD. The safe speed monitoring, I believe, is PLD as well, and the safety scanners are PLD. It specifies this in the manual for each KMP.
Thank you. Another one, what is the methodology for laying out a path? Is it magstrip or GPS?
So we use SLAM on all these AMRs to map an area. So first, before we have the AMR moving, we have a remote controller that we plug into the AMR. We drive it around in your environment, and it's going to create a map. And based on that map, the AMR knows where it's at. So it's not GPS. We can use color lines on the floor. We can also do QR code, but our main method is SLAM.
Thank you. I think that kind of goes along with this next one. Someone asked, is the setting up of your path geometry handled in Fleet Manager, or do you just create generic racks/charging stations and the physical track will take care of the path?
I'm not sure. I don't know. I don't. So you create your rack models for the AMR to detect them. I'm not sure if I understand the question correctly, but you create your rack models to for the AMR to detect them. It's going to go in, pick it up if it sees it correctly, and then it's going to do the pathing itself. It's not really related to the models. I don't know. If I didn't answer your question correctly, reach out to me and then we can discuss this in more details.
Thank you. Someone said that they have an AMR with a top plate and one without a top plate. They both share the same path. How can I change the default OBS plan for specific AMRs?
Very good question. This is so when you change the AMR size on KUKA AMR suite, you're changing the AMR size per vehicle. So each AMR can have different size. On KUKA AMR fleets, the fleet manager, it considers them the same type. So it doesn't know their different sizes. And this is something we're working on. We're going to introduce different types of so subcategories of the AMR types in the future. So you can have 1500p-1 or 1500p type A, 1500p type B, and so on to differentiate between these AMRs.
Thank you. Might have time for just a couple more. Do you have, or I guess, do you do any fusion of laser and camera data if one sensor detects an obstacle and the other sensor doesn't?
To be honest with you, I don't know how the internal algorithm works. I know they use both the scanners and the cameras to detect obstacles. So if any of them detect an obstacle, they will stop. But as far as the implementation, I can't really say much.
Thank you. All right, it looks like we are coming up on time here. So if you have any additional questions, I went ahead and put Mohammed's email address in the chat. So please feel free to reach out with any additional questions that come up. But thank you for listening to Mohammed today on our webinar session. And we will see you again on the next one. Thank you, guys.
Thank you.
Making automation easier.